Did you know there are an estimated 4,000 different species of snakes crawling across our planet today? From the powerful pythons to the venomous king cobras, these creatures are masters of their environments. But they weren't always like this. In the distant past, snakes had 4 legs, resembling lizards. Over millions of years, they evolved into the magnificent specialized predators we see today. In this episode of Wild Lineage, we'll explore the key evolutionary transformations that shaped snakes into the formidable hunters they are now. From the loss of limbs to the development of venom, and even the rise of legendary prehistoric giants like Titanoboa. Welcome to Wild Lineage, Episode 3. Our topic today is snakes. Around 167 to 100 million years ago, during the Middle Jurassic to Early Cretaceous, the earliest ancestors of snakes were not the limbless creatures we see today. Instead, they were 4-legged, lizard-like reptiles that hunted in forests, riverbanks, and burrows. These primitive snakes are believed to have evolved from burrowing lizards, gradually adapting to a more elongated body shape suited for navigating through tight spaces. One of the most fascinating early snake-like creatures was Tetrapodophis amplectus, a small, elongated reptile with 4 well-developed legs. Unlike modern snakes, Tetrapodophis still relied on its limbs, though its body was already shifting toward a more serpentine form. Its flexible spine and elongated ribs hinted at what was to come, the transition toward a completely limbless body. As these early snakes evolved, they adapted to new environments, from dense undergrowth to underground tunnels. This shift in lifestyle marked the beginning of a major transformation, one that would eventually lead to the complete loss of limbs and the rise of true snakes. Around 120 to 90 million years ago, during the early to late Cretaceous, the ancestors of snakes underwent one of their most significant evolutionary transformations, the gradual loss of limbs. This adaptation wasn't sudden. It was a long and complex process driven by their changing lifestyles and environments. Early snake ancestors were burrowers or semi-aquatic predators, and limbs became more of a hindrance than an advantage in these environments. As these reptiles adapted to squeezing through narrow tunnels underground or slithering through dense vegetation, natural selection favored individuals with smaller, less developed limbs. Over millions of years, their legs shrank in size until they eventually disappeared altogether, leaving behind only vestigial remnants in some species. Fossils of Najash ryonegrina, a snake-like reptile from 95 million years ago, provide crucial evidence of this transition. Unlike modern snakes, Najash still had functional hind limbs, suggesting that early snakes retained their legs for a time before they completely vanished. Another important species, Dinoloesia patagonica, had a long, flexible body adapted for burrowing, reinforcing the idea that the loss of limbs was closely tied to a subterranean lifestyle. This shift allowed snakes to develop their signature movement, lateral undulation, enabling them to glide effortlessly across different terrains. It also opened the door for future adaptations, such as enhanced muscle control and the ability to stretch their jaws wide to consume large prey. Though modern snakes no longer have external limbs, their evolutionary history is still imprinted in their DNA. Some species, like boas and pythons, still have tiny pelvic spurs, vestiges of their ancient legs, a reminder of the incredible transformation that shaped them into the masters of movement we see today. Around 90 to 70 million years ago, during the late Cretaceous, as snakes adapted to new hunting strategies, their skulls and jaws underwent a radical transformation. Unlike their lizard ancestors, which had rigid skulls and limited jaw movement, early snakes began developing highly flexible skulls, an adaptation that would redefine how they captured and consumed prey. One of the biggest innovations was the kinetic skull, where bones became loosely connected by ligaments, allowing for an incredible range of motion. This meant snakes could open their mouths far wider than any other reptile, an ability crucial for swallowing prey much larger than their head. Instead of chewing, they developed a walk the prey feeding method, where each side of the jaw moves independently to pull food into the throat. Another key development was the quadrate bone, a specialized hinge-like structure that gave snakes their famous unhinging jaw. This adaptation allowed them to engulf prey whole, whether it was large rodents, birds, or even other reptiles. Over time, the structure of their teeth also changed. Many species evolved rear-facing teeth that prevented prey from escaping once captured. Fossils of species like Dinoloesia patagonica and early boas from the late Cretaceous reveal how this transformation took place. Some early species still had rigid skulls, while others showed the beginnings of increased flexibility, bridging the gap between lizard-like ancestors and modern snakes. By the time Titanoboa, the largest snake ever, emerged around 60 million years ago, snakes had already perfected their jaw mechanics. This evolution allowed them to become dominant predators, capable of taking down prey far beyond what other reptiles of their size could handle. With their uniquely designed skulls and flexible jaws, snakes secured their place as some of the most efficient predators in the animal kingdom, a trait that continues to define them today. Around 60 to 40 million years ago, during the Eocene epoch, snakes took another evolutionary leap, developing some of the most advanced sensory systems in the reptile world. As they adapted to nocturnal hunting and tracking warm-blooded prey, some species evolved infrared heat-sensing abilities, an adaptation that gave them an incredible advantage in the wild. The key to this development lies in pit organs, specialized heat-sensitive structures found in certain snake families, particularly boas, pythons, and pit vipers. These organs, located between the eyes and nostrils, detect infrared radiation from warm objects, essentially allowing snakes to see heat. This adaptation was crucial for hunting in low-light conditions, giving them a thermal map of their surroundings. But heat vision wasn't the only sensory upgrade. Snakes also developed an incredibly refined Jacobson's organ, or vomeronasal organ, which allowed them to taste the air. By flicking their forked tongues, they collect scent particles and transfer them to this organ, helping them track prey, identify predators, and even find mates with astonishing precision. Another key adaptation was their ability to detect vibrations. Since snakes lack external ears, they do not hear in the same way mammals do. Instead, they rely on their lower jaw bones and specialized inner ear structures to pick up ground vibrations. When an animal moves nearby, the vibrations travel through the ground and are picked up by the snake's jaw, which transmits the signals to the brain, effectively allowing them to hear through the earth. This ability is particularly useful for ambush predators, helping them sense the presence of prey or even approaching threats. Fossil evidence suggests that early species like Madsoya, a massive prehistoric snake from the late Cretaceous, relied heavily on these sensory adaptations for ambush hunting. Later, apex predators like Titanoboa likely used a combination of heat detection, chemical sensing, and vibration sensitivity to dominate their tropical swamp environments. With these powerful sensory upgrades, snakes became even more efficient hunters, capable of detecting prey through body heat, chemical trails, and vibrations. These adaptations continue to define modern species, from pythons lurking in dense jungles to rattlesnakes striking with deadly precision in the dark. Around 50 to 40 million years ago, as snakes diversified into different habitats, they developed one of their most crucial survival tools: camouflage. Unlike their early ancestors, which relied on burrowing or speed to evade predators, many modern snakes evolved to blend seamlessly into their environments, becoming nearly invisible to both prey and threats. Camouflage in snakes comes in different forms. Some developed cryptic coloration, allowing them to match the colors and patterns of their surroundings. The gaboon viper, for example, has intricate leaf-like scales that make it nearly indistinguishable from the forest floor. Others use counter shading, where their bellies are lighter and their backs are darker, helping them break up their outline and stay hidden from both aerial and ground predators. One of the most fascinating adaptations is mimicry. Some harmless snakes, like the milk snake, evolved to resemble venomous species like coral snakes, deterring predators that associate bright colors with danger. This evolutionary trick, known as Batesian mimicry, is a powerful defense mechanism. Camouflage isn't just for protection, it also makes snakes more efficient hunters. Ambush predators like the death adder and the green tree python rely on their ability to remain unseen until their prey is within striking distance. Some even take it a step further by using caudal luring, where they wiggle their tail like a worm to attract unsuspecting prey before delivering a lightning-fast strike. From deserts to dense forests, camouflage has been a game changer in the evolutionary journey of snakes. Whether blending in or mimicking deadly counterparts, this adaptation has helped snakes survive for millions of years, proving that sometimes the best way to stay alive is to disappear. Around 30 to 25 million years ago, during the Oligocene epoch, snakes developed one of their most lethal adaptations: venom. While early snakes relied on constriction and ambush tactics to subdue prey, the evolution of venom gave them an entirely new method of hunting: chemical warfare. The origins of snake venom can be traced back to modified saliva. Certain lizards, such as modern monitor lizards and the Gila monster, produce mildly toxic saliva to weaken prey. Fossil and genetic studies suggest that early venomous snakes inherited this trait from a common ancestor shared with these lizards. Over millions of years, natural selection refined these toxins into specialized venoms that could paralyze, digest, or kill prey more efficiently. Venom glands evolved from regular salivary glands, and fangs became specialized delivery systems. Early venomous snakes had rear-fanged structures, meaning the venom glands were located deeper in the mouth. This trait is still seen in some modern species like boomslangs and hognose snakes. Eventually, evolution produced front-fanged vipers and elapids, which include today's deadly species like cobras, mambas, and rattlesnakes. Not all venoms work the same way. Neurotoxic venom, found in cobras, mambas, and sea snakes, attacks the nervous system, causing paralysis and respiratory failure. Chemotoxic venom, found in vipers and rattlesnakes, destroys blood cells and tissues, leading to internal bleeding and organ failure. Cytotoxic venom, seen in some cobras and vipers, causes severe tissue damage, leading to necrosis. One of the earliest known venomous snakes was Protheris, a primitive viper ancestor that lived in Africa around 25 million years ago. As venomous snakes continued to evolve, they became dominant predators in a variety of ecosystems, from dense forests to arid deserts. By the time the Miocene epoch, about 20 million years ago, arrived, venomous snakes had diversified into multiple groups, leading to the rise of species like the gaboon viper, king cobra, and rattlesnakes, each perfectly adapted to their environments with specialized venom suited for their prey. The evolution of venom marked a turning point in snake history, allowing them to take down larger prey while minimizing the risks of prolonged struggles. Today, venomous snakes make up a significant portion of snake diversity, with over 600 species capable of delivering lethal bites. This deadly innovation solidified snakes as some of the most efficient predators on Earth, silent, swift, and armed with nature's most potent biochemical weapons. By the time venomous snakes had established themselves as dominant predators, snakes as a whole had already begun their global expansion. Over millions of years, they diversified into a wide variety of forms, adapting to nearly every environment on Earth: deserts, forests, rivers, oceans, and even underground burrows. Some snakes, like boas and pythons, retained their ancestral method of constriction, while others, like vipers and cobras, perfected their venomous hunting techniques. Arboreal species developed elongated bodies and prehensile tails, allowing them to move effortlessly between branches. Meanwhile, aquatic snakes evolved flattened tails and the ability to hold their breath for extended periods, paving the way for sea snakes that now dominate tropical oceans. One of the most remarkable adaptations occurred in colubrids. The largest snake family includes species like rat snakes, king snakes, and racers. Unlike their more specialized relatives, colubrids developed versatile body plans and hunting strategies, allowing them to thrive in diverse habitats. By the Miocene epoch, around 20 million years ago, snakes had fully established themselves as top predators across the world. Some, like the Titanoboa, grew into massive, constricting giants, ruling prehistoric swamps, while others, like the ancient sea snake Paleophis, conquered marine environments. The evolutionary arms race between snakes and their prey continued to drive adaptations: faster strikes, deadlier venom, stronger muscles, and better camouflage. Today, snakes exist in nearly every part of the world except for Antarctica, showcasing one of the most successful evolutionary stories in vertebrate history. From pythons crushing prey in the jungles of Asia to rattlesnakes sensing vibrations in the deserts of North America, the legacy of their diversification continues to unfold. From four-legged lizards to the limbless, stealthy hunters we see today, the evolution of snakes has been a story of adaptation, survival, and mastery over their environments. Through millions of years, they have shed their limbs, refined their senses, developed lethal venom, and perfected the art of camouflage, each transformation making them one of nature's most efficient predators. But their story isn't just about survival. Snakes have shaped ecosystems, controlled prey populations, and even influenced human cultures and myths. From the ancient Titanoboa, the largest snake to ever slither the earth, to the modern vipers and pythons that rule their domains today, these creatures continue to thrive across the world. Their journey is far from over. As environments change and new challenges arise, snakes will continue to evolve, adapting in ways we can only imagine. This has been Wild Lineage, Episode 3, Snakes, Evolution of the Serpents. Thanks for watching, and be sure to join us next time as we explore the next great lineage in the story of life on Earth.